Hello, I'm Jack. Welcome to my channel, Practical Programming with Dr. Su. In this video series, you will learn everything you need to get started with WGPU graphics programming in Rust. In the last few videos, I explained how to create some simple graphics and primitives. In fact, all of those graphics objects are flat and two-dimensional. We have not created any real 3D graphics yet. In this video, I will explain how to create a 3D cube with distinct face colors. As shown here, you can see each face has different color. This is the first real 3D object we are going to create in a WGPU application. This example involves a lot of code and mathematics, so please get ready to digest it. In order to create a real 3D object in WGPU, you need to have the mathematical background on 3D matrix and 3D transformations. Since our computer screen is two-dimensional, it cannot directly display 3D objects. To view 3D object on a 2D screen, you must project your object from 3D to 2D. That will involve a series of coordinate transformations. As shown here, you can see that we define our 3D objects in the object coordinate system here. We then perform various transformations on the object, including scaling, translation, and rotation. We call this transformation as a model transform, like this. After this transformation, we convert this object in the object coordinates into the world space. Next, we perform the view transformation. This transformation locates the viewer in the world space and transform our 3D object into the camera space. This camera space also called eye coordinates. Next, we perform the projection transformation. The purpose of the projection transformation is to define a view volume. Here is called view frustum. This frustum used in two ways. It determines how an object is projected on the screen. It also defines which portions of an object are clipped out of the final image. That is, only the portion inside this frustum will be kept, and anything outside of this frustum will be clipped out. Finally, we use the viewport transformation to convert the clip coordinates into the normalized device coordinates that will actually be used to draw the object on our computer screen. In WGPU, the viewport transformation is automatically performed in the Vertex seeder code. Please note that, like WebGL and WebGPU, the WGPU API does not provide any functions for working with transformations. In this video series, I will use the CGMath create to create 3D matrix operations and transformations in WGPU applications. This create define various structures, including vector 2, vector 3, and vector 4, and also the matrix 2, matrix 3, and matrix 4. This structure allows you to perform matrix operations and transformations on 2D, 3D, and 4D. Since the 3D matrix and transformations are common for any computer graphics programming, here I suppose you already have the mathematical background on graphics programming. I will not spend any more time on this. Instead, I will concentrate on how to create 3D objects in WGPU applications. If you really need to refresh your mathematical background on 3D transformations, you can take a look at my recently published book called Practical GPU Graphics with WGPU and Rust. And you can read through the chapter 5 where I provide the details on how to construct a model, view, and projection matrices, and how to perform various coordinate transformations. Here is the content of the chapter 5 of my book. In this video, I will show you how to create a 3D cube with distinct face color. From this example, you will learn some of important concepts in WGPU, that is, uniform buffer and binding group. We will use the uniform buffer to represent the transformation and projection matrices, and then use the binding group to pass the uniform buffers to the vertex shader. Here, we will use the gate tool to clone the source code used in the last example, and then make changes to this source code to build the project used in this video. Now start Visual Studio Code directly from Windows Start menu. This is the Visual Studio Code interface. Now let's start a new terminal window and cd into code folder. Now make a new directory called WGPU07. Make directory. Okay, the new WGPU07 folder was created successfully. Now cd into it. We can then clone the source code used in the last video with the command git clone is WGPU06. After this command, leave a space and a period. This will place all our source code in the current folder. Now run this command. Okay, we can check direct. You can see here the code is indeed in our current folder. Now open this folder from Visual Studio Code. Open code WGPU07. Here contains all the source code used in the last video. To create 3D objects in WGPU, we need to introduce 3D matrix and transformations. Add a new Rust file called transforms.rs to the src folder. Add a new file called transforms.rs file. And we need to add some code to this file. Here we first define a structure called init WGPU. This structure contains our WGPU initialization related code. We also implement a new method called init WGPU to this structure. This initialization code will be the same for different WGPU applications. You can see we create an instance, surface, adapter, and configuration. All this code we have used before. So this code is the same for different WGPU applications. So we can use this structure and methods to avoid the code duplication. Next, we define a constant matrix here. We called OpenGL to WGPU matrix for coordinate transformation. This is because WGPU is based on DirectX and metals coordinate system. In normalized device coordinates, it defines x, y value range is -1 to 1. Z range from 0 to 1. However, we use CGMath is built for OpenGL. The coordinate system used in the OpenGL is defined x, y, z in the range of -1 to 1. So the difference is z component here. In our WGPU is 0 to 1, but for OpenGL, this is from -1 to 1 here. This the constant transformation matrix can convert the coordinate system from OpenGL to WGPU. We then define a create view projection method. This method takes camera position and look at direction, up direction, aspect ratio, and is perspective parameters as its input arguments. Here is perspective parameter lets you specify whether the projection is perspective or orthographic. Inside this function, we first create a view matrix by calling this lookat RH function defined in the CGMath create. We then create a projection matrix by calling perspective or also depending on the parameter is perspective. You can see our projection matrix is multiplied by this OpenGL to WGPU matrix. It's a constant matrix. This make sure we are in the right coordinate system. This function returns three matrices. You can see one is a view mat, one is a projection matrix, and another one is a view projection matrix. This view project matrix is a combination of the view and projection. Other functions, for example, create a view, create a projection, lets you easily create separate view and projection matrices. Finally, we use create transforms methods to construct our model matrix that contains, you can see, translation, rotation, and scaling. Okay, now we can save this file and close it. Next, we want to create the vertex data for our cube. From this figure, you can see that our cube has 8 vertices and 6 faces. If each face has a different color, each vertex will then have 3 different colors. For example, you see the front face here is one color, right face another color, top face different color. So each vertex will have 3 different colors. Here is the front face, A, B, C, D, A, B, C, D. This is the coordinates here. As we did before for a square, now we can divide this front face into 2 triangles. Here A, B, C is one triangle, C, D, A is another triangle. So in the same way, we can perform triangulation for the other faces. Now add a new Rust file called vertex data.rs to the src folder, and a new file called vertex data.rs. First, we need to create vertex positions using the create position methods. Here you can see for each face, for example, front face, we have 6 vertices. You can see 1, 2, 3, 4, 5, 6. Because each face is made of 2 triangles, these vertex coordinates are consistent with this figure. Next, we need to define another method called create color. You can see here, each face has a different color. For front face, all the 6 vertices has the same color. You can see the front face is blue, right face is red, and the back face is yellow, and so on. Now we can save this file and close it. Now we need to make some changes to our seeder code. From SRC folder, open the seeder.wgsl file. Here we need to replace its content with the new code. You can see this seeder is different from that we used previously because we need to incorporate the uniform buffers that store the transformation and projection matrices. Here you can see we first define a uniform structure. This structure contains model view projection matrix. Here is a 4x4 matrix. And then use the binding group here to pass the model view projection matrix to the seeder. You can see here the variable type is uniform. Inside the VS main function here, we process the vertex positions by multiply this model view projection matrix. The other code is similar to that we used before. This is the seeder we are going to use to create our 3D cube. Now we can save this file and close it. Next, we need to make some changes to the main.rs file. From SRC folder, open main.rs file. We need to replace its content with the new code. Here we first define the vertex structure that contains 2 fields. One is position, one is color. We then implement a helper function called vertex. This function can be used to convert 2 input parameters of I8 array into the vertex structure. This allows you to simply enter the integer as input without needing to type the floating point for the vertex data. You can see before here we use the integer, not a floating point or number. So this input becomes much simple. So this method just convert the integer into the floating point. Next, we implement another function called create vertices. Here we first call the cube positions and cube colors to get the vertex data, and then use this data to populate the vertex vector. You can see we define a vector of the vertex structure. Here we put the data into this vertex vector. This will be used to create our 3D cube. We then use a WGPU macro called Vertex Attribute Array to create an implementation block that creates static methods called here DESC. This method returns vertex buffer layout. You can see vertex buffer layout. In our example, this array here contains 2 elements. One is for the position, another one is for the color. Inside the state new function, we initialize the WGPU by calling the transforms and init WGPU method. Note here we use a wait keyword here when we're calling our async init WGPU function. This means that the application will suspend execution until the result of future is ready. Next, we construct a model view projection matrix. You can see by calling create transform to get the model matrix and create view projection methods to get our view projection matrix. We then create a uniform buffer to store our model view projection matrix. You can see the usage here is uniform. But we cannot use MVP mat directly in this uniform buffer because MVP mat here is a matrix 4 type, and the portrait is not implemented for this type. As a workaround, we convert MVP matrix into the MVP reference. This MVP reference is a F32 array with 16 elements. Since the array type is a pod itself, so it can be used to create our uniform buffer. You can see we create a uniform buffer use MVP refer here. Next, we create a uniform binding group layout and a uniform binding group, and then register our uniform binding group layout using the pipeline layout. You can see create pipeline layout using this uniform binding group layout. Next, we create a render pipeline by calling create render pipeline method. The most code of this pipeline is the same as we used in the last video, but we set here specifically the depth stencil attribute. Before we set this attribute to none, but now we set it using this code. If we set it to none for our example here, we may get unexpected and strange results. The depth stencil attribute tells WGPU when to draw over a pixel and when not to. In order for the depth stencil attribute to work, we also need to create a depth texture. Here you can see we create depth texture and also depth view. Use this depth texture. And then add this depth view to the render path descriptor. Before we only have color attachments, but right now we have depth stencil attachment. Before we set depth stencil attachment to none, right now we need to use this code. Finally, we also need to set uniform binding group to the render path. You can see here, render path set binding group. So use our uniform binding group. So set to the render path and call the draw methods to create our cube. The code for our main function here is the same as that we used in the last example. So now we finish the modification to this file. We can save this file. Up to now, we have completed our programming. Now we can run the following command in the terminal window to create our cube. Open the terminal window and run cargo run. Here is our cube with distinct face color. And we create this cube use the perspective projection. We can also change the constant in the is perspective. We set it to true. This means we use the perspective projection. We can also set it to false and save this file. Close this window and rerun cargo run to recreate the cube. Now you can see this generates our cube with the orthographic projection. Now we completed this example. In next video, we will discuss how to animate this cube. Thank you for watching.